Started. How is assignment 1? Terrifying. It's good?
Yeah.
Like double good?
Yeah.
Wow. Yes. Frustrating. Okay. All right. How many of you have completed assignment 1? Okay. People who completed, like, is it frustrating to you? Yes. Okay. Why?
My algorithm keeps outputting strings that are only negative.
Okay. Is that a mistake in logic or is that something else?
I mean, that's a mistake like in my programming.
Okay. So that's on you. All right. What about you? What is the reason for frustration?
It definitely could be an issue with like what I was doing, but like the data set was a little frustrating.
Like the size of the data?
The size of the data, but like also just like how some of it was organized.
Like the data set that is provided?
Yeah.
Okay. The organization is a problem, right?
For some reason, I kept getting like on only one column like weird like tree generation. Whenever like I removed that one specific column or like binned it, even though it wasn't a continuous variable, like it would run, and I wasn't sure. It could definitely be something wrong with my phone.
On that, I think actually the paper y'all gave us in correspondence to the data set, I think it's missing one of the columns. Like I was able to count 40 non-label columns.
39?
You know, oh no, I was able to count 41, but then the paper you gave us had like 40.
So it's like, sir, the data set has 42, the columns, like, and the labels are only 40. We're missing 2 of them.
Well, one of them's target variable.
Yeah,
so
target variable. Maybe
I think one's missing. And the one's missing
That's
is
what I
the
was trying to
24.
figure it out.
It's index 24
Yeah.
in the data set is the one that's missing.
So 24, is that like there was one column that was in the data set mentioned like you should not use that? Is that 24?
I don't know about that.
Like, we're not sure about like which particular data is missing, but there is like the lengths don't match, the key labels and the data sets indexes don't match.
Yeah, so in the data set, if you read the description, one attribute is forbidden to use.
That might be it.
Wait.
Yes?
It's called
This is weight, yeah. And that one has probably been discarded from that.
Maybe we should look into that.
But whatever is given, like use that. I mean, it should not be a big problem. I mean, in terms of implementation and getting an accuracy, what was the biggest hurdle? One thing could be the pre-processing of data. For example, if it's let's say a code, like a zip code, and you treat it as a continuous variable, then the decision tree is going to create trees like many different attribute splits and all that. It's going to get crazy. So convert that into a string, then it becomes a categorical variable. That would make your life much easier because you don't want to treat a zip code as a number. Yes?
So, for me, I think it's just the most frustrating point is my split function. It's hard to find the best split with the data that is not numbered.
So when you come to machine learning, so one big part will always be dealing with your data, cleaning, pre-processing your data that can be actually used by a particular model. So this is something like every day you have to do. Whenever you build you take a data set, you want to apply to a particular algorithm. Maybe that algorithm takes data in a particular format and the data you collected does not directly match. So data cleaning, pre-processing is a big part of machine learning project. So you should not think of it as an extra work that you are doing. This is just part of the process. But as you move forward, you will get better and better at this in data pre-processing and all that. And it will take much less time in the next assignment and so on. Yes?
And then for the attributes that like you could make them discrete, like but there'd be like 1,000 different values, or you could do buckets. Like, do you think it's just reasonable when you're coming to it, like just realizing that like making it discrete doesn't actually give you a lot, so you can just ignore that variable. It's just not as helpful as the clearly discrete variables, given we're dealing with a strategy that relies on.
So feature selection is not something that we are yet doing, right?
Okay.
So I would not say like don't use an attribute, but feel free to discretize or not discretize based on what you want, right? All right. In case you are running out of time and you think like running this, like how many instances, 250, 200K training? Yeah, so if you think like it's taking too much time and you're running out of deadline, try to sample the data set, make it smaller. If you cannot, I mean, it's best if you can, but if you cannot, try to sample some training, and testing has 100K, right? Around? Or no? Almost. Yeah, so sample maybe 50K or maybe 10K if you are running out of time. Okay? I will instruct the TAs to give you like minor penalties in that case. It will not be a big penalty if you are sampling and downsizing your data set, just to make it work and catch the deadline. All right? Okay, so let's get started. Evaluation and model selection. So in the last class, we kind of started on evaluation, and we talked about evaluation metrics. So tell me the name of 3 evaluation metrics we talked about in the last class.
Accuracy, recall, precision.
All right, everybody knows that, right? So accuracy, precision, recall. All right. What is accuracy? Yeah.
Are correct predictions out of everything.
What is happening here? Okay, this way. Yeah, sorry.
Are correct predictions out of all of our predictions?
Okay, so the number of correct predictions you are making, the proportion of the correct predictions, that is accuracy, right? And what is the problem with this? Yeah.
If you have like a very unbalanced set where it's like 99% one and 1% the other, you can just guess like yes, and you're right most of the time. It's so very high.
So accuracy is not a good metric for imbalanced data. That's the problem, right? Okay. So for imbalanced data, there is a minor class and there is a major class, right? I mean, there is an imbalance. So to handle those minor classes, because you want to, maybe the minor class is the most important one for cancer, let's say, less than 1%, but that is the most important class you want to focus on. So for the minor class, we have spatial metric to actually capture their importance. And such 2 metrics are precision and recall that we talked about, right? And we can compute precision recall for each particular class. But because the minor class is so imbalanced, we focused on the minor class, like label 1 in our lecture last time, right? So tell me, what is the difference between precision and recall? In plain English. Yes.
How many of the things you said were positive were actually positive?
And recall?
And recall is how many of the actual positives you got right?
Right. So there are 2 different things, right? One is, I am claiming that these are positive. And out of that, I'm claiming how many are actually positive. The set is entirely within what I am claiming. It has nothing to do with the actual truth. I mean, it has something, but it doesn't cover everything, right? Whatever I am claiming, like these are the attributes, but these are the data points I'm talking about. Precision only cares about that set and looks at how many of them are actually, I made a correct prediction. Although I'm claiming them to be positive, are they really positive? How many of them are? But the recall is about the actual truth of the data set. Like actually how many positives are there? And out of that, how many I actually could capture? So what is wrong if I just report precision or just recall? What can go wrong? Yes.
Like if you only do precision, then you would not want to guess a lot, because if you guess like a really small amount, then you're probably going to be right every time you guess. So precision doesn't really, only doing precision doesn't reward the actual behavior you want, and you have similar issues with recall.
Okay, so it's more about being conservative. You can be very conservative, and you can just be very selective when you say yes, it's a positive. And then your accuracy will go up in terms of precision, right? Your precision will go up because you are very conservative, and without being 100% sure, you are not committing to a precision, like a positive label. In that process, you will attain a high precision, but you will miss a lot of positive examples that were not so sure, but probably are also positive. So there is a trade-off. The more conservative you become, your precision goes up, but your recall goes down. And otherwise, if you become very open, like everything is positive, your recall goes up, but your precision goes down. So now, as your precision goes up like this, your recall kind of goes down like this. So you need to find a right balance that has a decent recall and a decent precision to really claim you have a useful accuracy number. Is that clear? All right. So we actually created this table to better define these numbers, right? So in one axis, we had true labels. So think about this play tennis data set, right? Play tennis. Right? So, example. True label. And then predicted label. What you are predicting. Right? And the predicted labels are also here. So you could either predict yes or no. Here the true label could be yes or no. Right? For example, here, example number 1, 2, 3, and so on. The true labels could be yes, yes, no, so on. And you could predict yes, you could predict no, you could predict no, and for some no, you could predict yes, right? This is the actual data set that is given, and these are the predictions after you have built your decision tree. That's what you are getting, okay? Any model, any machine learning model. Now you need to just quantify how good your predictions are. We could compute accuracy by just looking into how many times I got it correct. I got it 2 times correct out of 4 cases, let's say. So my accuracy is what? 50%, right? Because 2 out of 4, I got it correct. But then we said it's a problem when it comes to imbalanced data. So let's say I have only 2 cases of no and then 100 cases of yes. Then that's a problem. So we create this confusion matrix that gives us other metrics to consider. So this case, when the true label is yes, and I'm also predicting yes, that is called true positive. TP. Okay? This is called this case, when the actual label is no, and we are also predicting no. So that is true, negative, Tn. And again, just to be consistent, let me replace yes and no with positive and negative. Okay. Positive, negative, predicted positive, predicted negative. All right. What is this row? I mean this cell?
False positive.
Yeah, so it's easy to get confused. The definition is in terms of what you are predicting. What is the label we are predicting here? Positive. What is the actual label? Negative. So because we are making a false positive prediction, it's the false positive, okay? It's a false positive. So which of these two is the false positive? Which one? Second or the last? Last one, right? Because here you are predicting yes. In terms of the prediction, the definition is actually done. Right? Okay. So what is this? False negative. All right. Any question on this confusion matrix? Okay. So now, what is the definition of precision in terms of this table? What should be our formula? Because based on these comparisons, we can assign labels. Because this one is a true positive. This one is what? A false negative. This one is a true negative. Right? This one is what? False positive. So by assigning labels to these examples and the predictions, now we can count the number of times we have true positive, number of times we have false negative, number of times for true negative, and number of times for false positive. Then these cells will be some numbers, right? We can count those numbers. After we count those numbers, what should be our precision formula? Or what should go in the top? What is our focus right now? What is the minor class? The positive, right? And then what is the accurate number there? The true positive, the number of times we actually predicted a positive example correctly, divided by the total number of time we are predicting it to be positive, right? Precision is in terms of how many times we are predicting it to be positive. It doesn't have to be what is the actual number of positive. And how many times we are saying like an example is positive? True positive plus false positive, right? This row is basically all we are predicting to be positive, right? So this is what we are predicting to be all negative. This is what is actually all positive. And this is what actually is all negative, right? So precision is the total number of times that we are saying the examples are positive, and this is what that row means. What would be the recall formula then? True positive divided by all positive, and all positive is this column, which basically means true positive plus false negative. Is that clear? Any question on precision, recall, accuracy metric? And what is the formula for accuracy based on this table? True negative, everything, right? I mean all the examples. False positive, false negative, the whole matrix. That is what your accuracy is. Questions? So if you look at this figure, you can see this is a very nice illustration of precision and recall. So let's say this is the whole universe of examples, okay? It's like a box shape, just imagine, right? And then here is a decision boundary. Like these are all the positive examples, and these are all the negative examples. Like this is the truth, okay? And let's say we observe some data like this. Let's say something like this. That's what our data set looks like. Because these are kind of mistakes, noisy data. Although all of them should be positive, we had some errors in the data collection process, and we had some mislabels. And based on that, the model got confused, and the model learned that it's actually like a circle instead of a partition of the rectangle. Because this clearly covers the positive examples and separates the negative example, right? Whatever is inside, let's call it positive, and everything else is negative. So based on training data, you are still correct. But because in the real world, it is actually box, and we don't know that, we kind of had a wrong model that we learned, right? Now, based on this figure, tell me what portion is true positive? Positives on the left. So this part is actually true positive, right? Because this is where the model said it's positive, and they are all supposed to be positive, right? What is this part? False positive, right? Because the model is saying this is positive, but actually it's negative. So this is false positive. What are false negatives? Which ones? So this and this, right? These are false negatives. Yeah. So you can clearly see what it says basically. For precision, what we're looking at here is something like this. The whole circle and the green portion of the circle. And for recall, what you're looking at is again, the top ones are the same, right? The true positive. The bottom one is different. Here is the left portion of the rectangle. This entire portion, right? And that is why the recall is TP divided by TP plus Fn. Does that help? All right. Okay, so far whatever we have learned, or I think you have learned, how many of you have no clue what we have learned so far, what we have covered so far? Or how many of you don't even know what you don't know? You don't know what you don't know?
Right.
Good. That's where learning begins, right? So you are in the right spot to start learning. That's good. Okay, so let's say you have 100 examples, you have 5% are positive. if you just say no, your accuracy is 95%. But if you predict 4 to be positive and 96 to be negative, and 2 of them are actually positive, then what is your recall and precision? Anybody has confusion why the recall number looks like 2 by 5 and precision looks 2 by 4? Do you agree? Is this correct or not? So tell me, what is the number of true positive based on that description? 2. What is the number of false positive? 2. What is the number of false negative?
3. Why? Because we got 2 of them right about the positives. I mean, there's 5 totals. 5 minus 2 is 3.
Right.
So that means 3 of our negatives.
There are 5 examples that are supposed to be like in real positive, but you just figured 2 of them. So that's why recall is 2 by 5. Is that clear? All right. Let me switch my view. Okay, so we know these formulas. Again, this is the same thing. And we have seen this, right? It's just have the actual class and the predicted class flipped. The rows and columns are just switched, nothing else. We have seen all of this. But here is the point, right? I mean, precision and recall does not give you the complete picture. So you need to combine both of them. So what can we do? Sorry? What can we do to combine them? Yes? Yeah. What kind of formula? What's a good way to combine them? Sorry, add them? Add them? Okay, so I have heard add them. So tell me, is that a good idea to add them? Okay, but is that a good start? What can go wrong if you add them?
If it's so small that it doesn't make a difference anyway.
How about a model that has 1 precision and 0 recall? If you add them, you still get 1, but that model is not useful. Okay, you can say the limit is 2, right? Because 1 plus 1 could go to 2, but still you have 50% to a model that has 0 recall. Is that a good thing? Yes. You could take the average or you could take the minimum. Yes, better idea. If you take an average or a minimum. What is the problem with an average? Yes.
The average does the same issue as the sum.
With the sum, right?
Because you're just dividing by 2.
You are just dividing, you are just normalizing. It has the same problem as sum. Min, probably a better idea, but what is the problem with min?
It's still like accuracy divided by 2 and
So think about a model that has 80% accuracy, 20% recall. You are just saying it's a 20% model. Is that?
it's not much better.
I mean, it's debatable, right? So probably you want to have something where you want to weigh them in a more clever way. That's what F measure does. So that's our new metric, right? So now we are going to talk about the F measure. And this F has nothing to do with the bad word, okay? So F measure is basically combining precision and recall in some intelligent way. And there is no right answer here, because maybe in your particular domain, precision is more important in your application than recall. Maybe 80-20% minimum makes sense for your application, maybe. So it's good to give the user the control over how much importance you should put on precision versus how much you should put on recall. And that's what F measure does. And the formula looks something like this. 1 plus beta square times precision times recall divided by beta square plus recall. Okay? The plus is not visible here. Now, based on the value of beta, you can put different weights on precision and recall. But if you want to put equal weight, what should be beta? Beta should be 1. And if beta is equals to 1, this formula will turn out to be 1 and 2 here. 2 times precision into recall divided by precision plus recall, which is essentially what? 1 divided by 1 by precision two, right? What?
The harmonic mean?
Yes,
Okay.
that is. Right. So, if you replace beta with 1, we call it the F1 measure, because beta equals to 1, which is the harmonic mean of precision and recall. That's a better way to combine precision and recall, because if one of them goes down, this metric drastically goes down. So it kind of tries to push both of them to be high. And this plot we have already shown, right? There is a trade-off. Like if you want to increase recall too much, you say everything yes, your recall will be 1, but precision will be 0. And here you're very conservative. Your precision is high, but recall is 0. So you want somewhere to be here. And this, if you plot F1 measure, it will look something like this trade-off. And you probably want to sample some point from here. Okay? Questions? Yes?
What's like the benefit of having like a different weight than 1?
It depends on your application. Let's say you want to have more weights on the precision than recall. Let's say. What do? You want one number. You want both precision and recall to be considered. But maybe precision should be a higher importance than recall to some degree. And you define that degree. How do you do that? Set beta to some other value, right? Because if you set it to 1, that gives equal weight to precision and recall. But then if you give some other weight, the weights you are defining, how they should be combined. And that maybe in your, for example, in cancer, which one is more important, precision or recall? Which one? Okay, so
recall, because it's really important that you get it right.
Yeah.
but
Like
what
in
about
case of cancer.
what about you tell a lot of people who doesn't have cancer like you have cancer?
That's bad.
That's fine?
I'd rather get people that, like, get everybody, right? Versus me say, you don't have cancer, you have cancer. I'd rather.
Good luck talking to doctors.
Absolutely.
Good luck with you selling your software to the doctors. Yes.
You're gonna have to do some cost metric of how much it costs to hand out a false negative versus a false.
Yeah, so that beta comes from your business model. And I'm not a business person, unfortunately. You have to go back to that building. Like Hartgrave and what is that building? Louder Hall, and then there is another one, right? Go there and talk to them. What should be my beta? That I don't know. But if you tell me the beta, as a machine learning engineer, I can compute this matrix and give you a machine learning model. Does that make sense? All right. Okay, so far we have been talking about just one classifier and telling how good or bad that is. But is that really the ultimate thing that helps us, or like we need more? We always need more, right? And it's more important to compare two classifiers or machine learning models than just saying, okay, this one is 60% good. But what does that give us if I don't have another model to compare with? Because then whether it's good or bad, that's the only model I have. But when you actually deploy some models in real life, you want to test it out across multiple possibilities and then make a decision, okay, which one you should choose actually, right? Because in reality, you never know what's the real data distribution looks like. All you can do is to gather some data, assume that's a good representative data, learn a model, and then start applying on real world to see whether that is actually giving you something important or not, which we simulate by using a testing data initially. But then it's very common that based on some testing corpus, people have decided, okay, this is the model to go, and then actually deploy on real world doesn't help. That happens as well. Okay? So the question is, now you have two classifiers, C1 and C2, and you want to know which one I should use. And you have learned two decision trees, right? C1 and C2 are basically two different decision trees. It could be a decision tree and a naive base. It could be a decision tree versus a neural network. It could be two different neural networks, anything. As long as you have two classifiers, C1 and C2. You want to know, and you have, let's say, one data set for now. You could have multiple, but let's say right now you have just one data set. How do you know whether C1 or C2 is better? What do you do?
Look at the testing accuracy of both the algorithms.
Testing accuracy, okay? Not training accuracy?
Both, to be honest.
Both.
Like, you compare.
Okay, what about just training accuracy? Can you just choose one algorithm based on training accuracy? Yes.
The validation set.
Wouldn't we use the validation set for that? Okay, yeah, definitely we can do a lot of things. So let's go step by step. Let's just say we have training data. And can we use training accuracy to choose between C1 and C2? Is that a good idea? No. Why?
I think because we need both training and testing data, or we might want to gather more statistical evidence from that.
Okay, why it's a good idea to look into testing data, just not training data?
It just gives us more predictions, gives us more algorithms.
Okay, but there is a particular term that we coined in this lecture already. What might happen if we just look into training accuracy?
Overfitting.
What?
Overfit.
Overfitting, right? Maybe one model overfitted a particular data set and the training accuracy is higher, but maybe in the real world, it will actually go down. So just by looking into training accuracy and deciding, okay, this model has a higher accuracy on training data is not probably a good idea. You need more. Okay? Okay, so the next suggestions were what? Testing data, validation data, that kind of setup, right? Testing data is definitely the ultimate goal to have a high accuracy, but you cannot use the testing data during training. So we simulate that process during training using validation data. So validation data itself is kind of a simulated testing data, right? You are just using that during the training process. So it's good to look into those unseen. The whole point is the model should be making prediction on some unseen examples to really understand whether it is actually generalizing or having a useful model or not. So the answer is clearly no. So what about the accuracy on testing data? Yeah, definitely a better idea. But let's say I have one data set, and based on that, I just get how many numbers on two models? How many numbers do I get? One data set, two models. How many testing accuracy we get? Just two. And is that robust enough just to look at these two numbers and say this is better than this? Why not?
Well, if you have a large set of values with different algorithms, you can pick the best one. But having two would be much naive approach, because you cannot decide between two. Like this is the best in every possible case.
Okay. Think about this. Just one test. Yes, go ahead.
I was going to say, testing data might just be biased. So
Exactly. Think about the quality of your testing data. If your judgment is based on only this testing accuracy, you are assuming this testing data is the perfect one. But then again, even if this is the perfect one, let's say one model has accuracy of 59.3 and the other one has 59.25. Which one is better? Which one? Which one is better?
Unless you do it 3 times and they're statistically significant, you don't know.
So you need statistical significance before you can make a judgment on this. But just based on 2 numbers, can you make a statistical judgment? You need more data. You see the point? So just looking at, maybe one way is use 50 different testing sets and try on 50 different testing partitions and look at these numbers on 50 different data sets and compute some statistics there. That's definitely a better approach. But often then we don't have 50 different data sets. We just have one data set. What do we do? Partition the data set. Exactly. You partition the data set. You kind of simulate that process, training, testing, different times with random partitions. And then you come up with these numbers for 2 different models. And then you compute some statistic to see whether they are actually statistically significant or not, the difference. Question on this? All right. So in the project, when you are actually analyzing this, implementing these methods, right? You will also have to report these statistical tests, whether this model is better than that model on your data set or not, using the techniques that we are going to talk about. And we are not going to talk about all the tests, but I can always give you pointers to more tests, and you can just quickly look up. And there are well-defined libraries. You can just use them to do that test, statistical test. Okay? So testing on accuracy accuracy on testing data is a definitely better idea, but there is a but, right? Whenever you have but, you can ignore what was said before, right? Before but. No? Okay, because the most important part comes after but. So basically you want to look at more than a single number. That's what I said. You need to compute a statistic. In order to compute a statistic, you need data. If you have just one data set, one way to create more data set is just by partitioning the data set. All right? So that's where k-fold cross-validation comes in handy. So instead of so let's say you have just one data set, right? No training testing, just you are given a data set. Now you need to create those partitions, right? So one way is just split it like 80% training, 20% testing. But that has this problem. Just one number, evaluation is not going to be robust. So what do? You split the data into k equal parts. And we talked about this k-fold cross-validation before as well. But here is like more like a visual representation of that. So you see it is equally partitioned into 5 different partitions. And you see like the red one is the testing partition for a particular fold, and the rest of it is simulated as training. Still we are using this trick of unseen data, right? Because the model is going to be trained only with 4 partitions. And then we are going to test it on the 5th partition, which the model has not seen. But then on the next one, we are going to retrain the model from scratch without the 2nd partition, just using partition 1, 3, 4, and 5, and then test on the 2nd one. Still we are doing preserving the requirement that you cannot train on testing data. That is separate. Okay? So now you have 5 different partitions. At least you have 5 numbers, which is better than just comparing one number. Right? But it still may not be enough, right? I mean, statistical significance requires more than 5 examples. Yes?
How is this? I'm not sure how this is exactly different from us using the validation set in the testing data. So
Validation set in the testing data or the training data?
The training data.
Right.
So when we do a validation set, we're taking, each time we do a validation set, a different split. So how is this?
So it depends on how you are creating this is essentially creating 5 different validation sets, right? I mean, think about this. When we actually want to have one golden testing set, that testing set, the red one that you see, just throw this off. Just keep it aside. Don't touch it. And now this partition that you see is only based on the training partition there. The test is untouched. Now here, the validation, we are just creating 5 times. You could also do it randomly, sampling and then dividing, right? That's another way. And 5-fold is one way like to ensure that all the data points are at least once part of the testing data. Yes?
So, like you have to divide the data set into k different parts, right? What if the length of the data set is like a prime number? Or is there any alternative way you would partition the data set?
It's more like an engineering decision, right? I mean, it's not a problem that if one partition has 31 examples and the other partition has 30. It doesn't matter.
Really matter.
No. It doesn't really matter. You just have to make a call.
Okay, so right now what you're showing is you have the training and you split the training up and then you're testing it on a split from the training.
Yes.
And then you're going from that data and testing on the test.
Yeah.
And then that's what we're going to be comparing these 5 different ways.
So now based on these 5 different partitions, you are going to learn 5 different models, right?
Yes.
Because your training partition is 5 different combination. And you are going to test it on the other partition, right? Each time while validation. And you can get 5 different validation accuracy, right?
Yes.
And based on that, whichever gives you the highest validation, pick that as your final model, test it on the testing data. Assume that that is your right model. But based on the validation data, numbers, accuracies.
So say I'm using K1, right, the first one. So when I get the accuracy or the model from that one, am I testing it on K2s?
No.
So it's just everything from K1s being K1 and then...
You can also test it out on K2s and all that, but you have that is not meaningful because you are then testing on data that you have already seen.
Yes, okay.
Right?
So then now instead of these 2 numbers, we just have 5 different accuracies.
5 numbers. 5 different pairs. Which is still not good enough for statistical test. So what could you do? Increase k. What is the maximum value of k you can use? Yes.
The number of items in your data set?
Exactly. You can have one example left and train on the rest of the examples, get one model, test it on that example. You could flip that problem. Why are you laughing? What is wrong with this approach? What? What?
You can do that, sir.
I cannot. Why?
You can. Like, that's a valid reason too. So you just put one and just train on the other.
Yeah.
And just test it on the last one.
Is that okay?
That's fine. But maybe we are too biased. Like the single test which we are performing might not always be correct.
Well, you are testing on each of them, right?
Yeah.
And eventually you will be looking at maybe an average.
Yeah.
Over biasing that last one.
Yeah.
But what is another problem with this? Think about a data set with billions of examples. You need to train billions of models. We don't have time. Right? So we have to strike a balance between what k you want to use versus the amount of statistical significance you want to get. Right? So maybe k is equal to 5 is not a good idea. Maybe k is equal to 10. Maybe k is equal to 30. Or maybe k is equal to 5 is still fine, but we need to maybe randomize each partition multiple times. Right? Think about this. This partition is coming from the plain training partition as it is. But if I randomly shuffle that training partition multiple times and then again do this partition, then that will be another kind of sample, right? And if I do that randomization 5 different times, now I have, and then do the 5-fold cross validation, then I have 25 numbers. That's, I think, n is equal to, there is this golden rule of statistics, right? If you are close to 30, probably that's okay. Right? No, I don't know who said this, but that looks okay to people. Right? So probably, or 10 different randomization and 5-fold cross validation, 50 numbers. That's probably good. Right? If you have 2 data sets, then you just need 225 partition, and then 2 data sets will give you 50 numbers. You are at your own, pick how you want to do that, but you get the point. So this is the example of 3-fold cross validation, right? You partition this, then you have the first partition, you have second partition, and you have third partition, and then you have some testing performance on that partition, and this testing is essentially validation, right? Don't confuse that. Okay, and then you want to compute some summary statistic over the k-test, right? But then if k is small, then we have this problem, so we can go to k is equal to n. That we talked already. That is not computationally feasible, right? Treat each example as your testing partition and rest of it as training. That doesn't scale very well. So what you want to do is kind of like make a trade-off. And the idea is to do randomization. So you first randomize the data set, and there comes a t number of times you do a trial. And t number of times you do randomization. Then you do, for each randomization, you do k-fold cross validation. So you get t times k numbers. Right? And that is a better set to compute some statistic over. Now the question is, what is that statistic? Right? So one popular statistic that people compare is t-test. That's what we are going to talk about. Probably if you have gone through probability statistics course, you already know about this term. How many of you know about t-test? How many of you have never heard about t-test? Okay, good. So these are called significance tests. and the significance is between difference between two numbers. Because you see, like the 25 different numbers you computed, what is the most obvious thing that you want to do based on those 25 numbers? Let's say, forget about significance test and anything. Just tell me you have two classifiers and you have accuracy numbers, A1, 11, 21, A12, A22, and so on. Right? So if I give you this, what is the most obvious thing you are going to do to compare these two sets of numbers? Yes? You take an average, right? Look at the average of, like, for C1 and look at the average for C2, and whichever is higher, that model is better, right? But does always a higher average mean that it is actually significant? At least in terms of the definition of statistical significance, it's not. That's where the significance tests come in. So if you compute a difference between the mean, is that mean actually really significant? That is that question I told you, right? 29.5 and 29.27. Let's say this is one average, this is another average. Now, is that significant? That difference, very, very minimal, but that could be significant, that could not be significant. You don't know until you do the statistical test. And that's what we are going to do. And one popular test is you can do is t-test based on those numbers. Okay, so essentially you are looking at the accuracy of A over n samples and accuracy of B over n samples and the difference. The question is whether the difference, you know which one is higher. That's not the question. The question is whether the difference is significant or not. Because you can always just look into, compare two numbers, you know which one is higher. But a higher number doesn't also essentially mean a statistically significant better model. Okay? So in machine learning and even like in statistics, this is called the hypothesis testing. So you basically have two different hypotheses. And each hypothesis is essentially your classifier, right? You are assuming that this classifier is the right one. And then you have another hypothesis that this classifier is the right one. Now you are basically testing which hypothesis is better. Because we don't know. And hypothesis is essentially our classifiers here. Right? Question is which one is better? So we need to be more specific when we say like what is the hypothesis we are going to test? And given these two hypothesis classifier, we make another hypothesis that these two hypotheses or classifiers are statistically different. Let's make that hypothesis that these two classifiers are actually different statistically. And we are going to test that hypothesis. And if that holds, then they are different. And if it doesn't hold, they are not different. And we can flip that hypothesis that they are different the other way. We could say they are not different and test it. And then if we could reject that hypothesis based on the test, then we could say they are indeed different. So see, two different hypotheses, right? And the hypothesis has a common term when we say like two different models are not, there is no statistical significant difference between these two distributions, two sets of numbers. It's called the null hypothesis. How many of you have heard about null hypothesis? Okay, so the null hypothesis basically says this set of number and this set of number are coming from the same distribution. They may look a little different at each row level and all that, but essentially they come from the same distribution. So they are not actually, although you see a difference in this, their averages and all that in individual numbers, they are essentially the same. Okay? So if we make that assumption that these two numbers are coming from the same distribution, which is the null hypothesis, then in order to prove that one of them is better, what do we have to do?
Have an alternative hypothesis.
Yes, or in terms of null hypothesis, what do we want to do? Accept or reject?
We're trying to find a counterexample.
Reject, right? Because null hypothesis is saying they come from the same distribution. There is no difference. But if we really want to show, like, for example, you come up with a new method, your search engine, right? And this is Google. And you want to say, like, mine one is better than Google. You want to show there is a statistical significant difference between these two accuracy numbers that you have. So essentially, you want to reject the null hypothesis that your accuracy numbers and the accuracy numbers from Google are coming from the same distribution. Okay? Now the question is, how do you do that? Essentially, what you have to do is to kind of compute a distribution, or like compute a statistic and test it out whether that statistic is consistent with the null hypothesis. So tell me if null hypothesis, yes, go ahead.
So could you do it by computing the accuracies on a whole bunch of different subsets of the testing data, get a distribution, and then do your test from there?
Yeah, you could do that, but then again, if you do all those splits and get all those numbers, eventually you have a set of numbers. Then what do you do on those numbers? You need a single number, let's say, to decide whether they are actually different or not. So the question is, here, think about this. They are essentially, if they are identical, what would happen? If they are exactly the same model, you test it twice, what will happen to these numbers? Deterministic models. Same number, what would be the difference?
0.
0. So if null hypothesis is true, now don't think about exactly same model, but two models that are almost similar, very comparable. They give almost similar accuracy numbers from the same distribution. So what should be the expected value of this difference?
3 times
Very close to
the standard
0.
deviation.
It should be 0. Expected value should be 0. Expectation of the difference between these two numbers. Maybe in one case this is higher, but maybe in the other case it will be lower. It will average out and become 0. That is when these two models are almost identical, right? So, actually if I try to create a distribution, forget about this, just about null hypothesis that any two models who are essentially the same gives you almost the same predictions. What should be the distribution that will look like for the difference between their two models in the accuracy?
About 0, like a circle around 0.
Circle? What kind of? Okay, what should be the probability that the expected difference is 0? Pretty high. What should be the probability that the expected difference is 0.05? They are almost similar model.
A bit lower.
Much lower. What about this?
Very much lower.
Pretty much lower. So it should be something like this. Right? Now, you can compute, so this x is just some statistic. For example, the expected value of the difference, that's what, if you want to put that, but you could compute more sophisticated statistic. The whole point is the expected difference for a null hypothesis case where the models are identical, it will have a pretty high accuracy for like pretty high probability for the number 0. Now, based on this data, if you compute some statistic that is, let's say, 0.3, what would be the probability here? Somewhere here, almost 0. That is less likely, right? It's not likely. Based on this distribution, it's not supposed to happen. So if null hypothesis is true, this cannot be true. But this is true, we know from the data. So null hypothesis is not true. So we reject the null hypothesis. That basically means there is a significant difference between the two methods. Okay? All right, so going into further theoretical discussion of what T distribution means and all that is beyond the scope of this course. But the whole point is you have this kind of many different statistics that you compute on this accuracy numbers. And based on that, you could compute some probability, which is called the p-value. How many of you heard the term p-value? Right? And based on that p-value, you can reject or accept null hypothesis. And that p-value comes from some distribution over some statistic. And if you have, let's say, a probability here, let's say that is, and often what we do is, if the null hypothesis is less than 5% probable, that is our, so we are 95% at least sure that we can reject null hypothesis. So there is a 95% confidence that our model is better, or the vice versa. So that's why a well-studied norm is to test it on 95% and 99%. So you want to be pretty sure. And when you report this model is better than that, you also want to report the confidence label, the confidence, the p-value that you are reporting. What is your confidence in that number? So, what is the statistic we are going to compute? This is what t-test look like. So essentially, based on your data set, you want to compute this t statistic, which is essentially the formula that you see is delta root over k, and k is essentially the number of examples you are training on. But it's not the number of example in your training data set. It's the number, like the t times k. You created this many C1, C2 numbers, right? So the total number, like we said 25 or 50 numbers we can create, that is the k here. This k is different. This is the parameter for the t-test. So the number of accuracy pairs that you created, that is your k here. And the delta is essentially the average of the difference in accuracy. So here, you are essentially looking at the difference between the average accuracy and each partition accuracy. You are taking a variance of that. But the whole point is, as I said, whatever metric you compute, the t distribution, this number, if null hypothesis is true, if two models are essentially the same, then this number should fall in a particular range. It should not be higher than that because of the underlying distribution we are assuming. And there is a table, t-test table, that tabulates those numbers. You can compare your statistic against that table and see whether that falls in the range or not. Okay? So just use that formula. For example, if you have 30 examples, so 30 accuracy pairs, and to get a 95% confidence interval, what you need to show is the absolute value of t is less than this. Okay? Then the null hypothesis holds. Those two models are same. But if it is higher than that, that means it's not coming from the same distribution. It must be coming from a different distribution with at least 95% confidence. Okay? So let me show you how to do this. So here is the algorithm. So you first compute the difference between the two observations. Then you compute the mean difference. Then you compute the standard deviation. And then you compute the t-statistic. So something like this. Let's say you have 11 partitions. Let's say 11 different training testing partitions, okay? And you have two models, and their accuracy numbers are like 3, 20, 3, 13, 3%, 13%, 12, 20, like that, okay? Now you want to compute a t-statistic on this number. What do? You first take the difference. You see the two accuracy number, you compute the row-wise difference. Then you compute their sum, because you need their average, the difference of the average of their performance difference, the delta. Okay, it's simple. These are just simple steps, and you don't have to actually implement this on your own. I mean, you can just use any existing packages, but I'm just showing the process. And then you compute their variance and sum it up. And you just plug in those formulas, right? And based on this data, you see that this t statistic is this. But forget this t statistic, but just look into a score 1 and a score 2. Which one you think is better? Which model? Score 2. Why?
It's a bit consistent.
Over each of the partitions, you can kind of see like score 2 scores higher most of the time, like maybe not in this case.
But the values are pretty consistent.
Right, right, and the values are higher consistently, right? So do you think they come from the same distribution, these two numbers, score 1 and score 2? No. And the t value, forget the sign because you just need to look at the absolute value, 2.74 actually tells you they are not coming from the same distribution, because there is a table that you can compare against. So you have 11 example, you need to do n-1 degree of freedom. So you need to look at the 10th row, and you are looking at 0.05, the two-tailed distribution. So you kind of go here. So this is the number you are comparing against. And the number we got is 2.74. Here is the number 2.22. So if null hypothesis was true, the t-statistic must have been less than this. But we didn't see that. We saw a higher number at this 5%, 95% confidence interval. So we can safely reject null hypothesis. That basically means score 2, which even if you compute an average, we'll have a higher average. But now we can say that average is actually significantly better than the average of score 1. So here is the argument, right? So the process is you first compute the degrees of freedom, which is total number of samples you have in your accuracy pairs -1. Then for this example, you look at the table and see what value you want based on your confidence interval. You compute your t value. You compare 2.74 against that 2.22. And what do you see is that this number is higher than that. So you can reject null hypothesis. So actually, we reject the hypothesis that there is no difference. When you reject that there is no difference, that means there is difference. Right? So now we move on to our next test, hypothesis test, which is, we don't have one today. All right? And we are not going to teach you more hypothesis testing, but there are. For example, Wilcoxon signed rank test. That is also a very popular test. And that is non-parametric. This one is a parametric test, right? You have the number of Ks and all the parameters. So, but you can always look up more tests and do them. But the whole point is you need numbers, accuracy numbers. You need to compute a statistic. You need to derive a p-value. And based on that, you need to make a judgment whether the difference is actually statistically significant or not. Thank you very much.